in the first it was clear.
Okay, so the recording started now, and we can continue now. Yeah?
Okay.
Okay, so we have now this shape these lines. Yeah, but this is only a geometry, of course. The next step is finite element method. The first fact of the finite element method, we have to divide this area into the small parts, elements, using meshing. Yeah, so we have the next step is to create a mesh. Yeah, that means we have this area. This is our model, and we have created a mesh on this model now. So here we are still on the first card, geometry and mesh, and we will use here in this second position this auto mesh, the planar mesh. Yeah, because we are meshing a planar region. So we will click on this. I can close this one, and here planar mesh now. Okay, and the mesh is generated using rectangles or triangles. Yeah, and I think the best option for this one is using rectangles, or not rectangles, but irregular rectangles. And I will write, for example, here divisions here 100 in the horizontal and 5 in the vertical direction. That means this is the number of divisions in the horizontal in the x direction, and this is the number of divisions in the y direction in this one. Okay, and now I can click on here quad mesh. But the software, of course, yes.
Did you put there 120, right?
105, yeah.
5. Second one is 5.
Because this distance is 200 and this is 10. So the dimensions in the horizontal and vertical direction of the element should be approximately the same. Yeah. So here 100 by 10 by 200 divided by 100 divisions, and here is 10 divided by 5 divisions. Yeah.
Okay.
So, and how I will create a quad mesh here.
Okay.
And nothing happens because the software don't know which area I want to mesh. Yeah, the area is given by these curves. Yeah, so he is asking me the curve list. Yeah, so I have few possibilities. Write all numbers of all curves here, or click on each curve and so on. This is not, but it's not, or choose all curves using the mouse. Yeah, just by typical normal selection, you know. Yeah, or use this one. This means all existing. This is, I think, the most useful possibility now. Yeah. So if I'm using for a list, I can choose this one. This means all existing. That means in my model are only these curves existing. So I will choose all existing, and now a mesh is ready. The mesh should be this mesh looks be okay. If I'm not, if it seems not so good, I can clear the mesh here on the bottom, and I can change anything here and try it again. Yeah. So if I leave, for example, 10, 100 and change the second divisions to, for example, 15, quad mesh, all lines. So we can see that that the elements are not so beautiful because they are distorted. Yeah. So clear mesh, 5 again, quad mesh, all existing. This is quite good.
Sorry, come again. How to remove the mesh? The first.
Here on the bottom, clear mesh.
Yes. Ah, okay. Yes, yes.
Yeah, yeah.
Yes, yes.
So you can try different numbers of divisions and so on, and you have to choose the mesh is good enough for the solution of the problem. Of course, the quality of the mesh is a theoretical problem, yeah, and to discuss about the quality of the mesh, we have to know many of the theory about the background of finite element method. So this is not in this course, yeah, discussed. So this is quite good mesh, yeah, what we have now, yeah. So 100 by 10 is okay. It's quite good mesh. Right? So,
sorry, before you continue, is there a place where maybe, because sometimes you could have geometries that have from very irregular shapes, sometimes you have the option of choosing the kind of shape you're expecting for the mesh, like maybe hexagonal or other kinds of shape for the mesh. Is it applicable?
Yes. Here you can use, for example, this one. This is a triangular mesh, yeah. So I can clear mesh, triangular mesh, all existing, and now it's meshed with triangles. You can see, but very poor mesh because we have 1, 2, 3, just only 4 triangles, yeah. So it's not good. And if I want use a different shape of elements, not the quads but triangles, I can use this one, but you can see the result is poor, unusable. So I can use, for example, curve divisions here. For example, 5 to this.
We can't see it. Can you just bring that window you open right now?
Sorry. So curve divisions here.
Yes.
Okay. And
Yes.
this window is a more general thing to define the divisions for the mesh generation. I can, for example, put divisions on each line in our model. Yeah. So number of divisions 5. Apply curve divisions, and I can apply it, for example, to these two lines using mouse, and using the right mouse button, I will confirm.
But first, we need to remove the first mesh, right? In
Yes,
this
yes. Sure.
Okay,
You have only one mesh. You can have only one mesh.
Okay.
So now I choose these 5 divisions. It's the same one like this 5 in the y direction 5, yeah. But this is more general because I can define the divisions on any line in the model, yeah. And for example, 100 now apply, for example, to this line. Okay. That means now the mesh will be generated using these divisions on these lines. And for example, 40 to these lines. And for example, 20 this line. And now I can close it and use this triangular mesh, and it's much more better than in the former case. Yes, because the mesh started with these divisions on the border. So in the planar case, you can use quad mesh or triangular mesh or a mixed mesh. Yeah, and you can see they are mostly quads, and maybe anywhere is a triangle. Here is not, in this model not, yeah, but it can be, yeah, because I use this possibility. Yeah, so it's up to you which type of elements you use and which mesh you will produce. Yeah, you have to know if the mesh is good enough or not, because the model or the software do not knows what you are interested in, yeah, and the quality of results depends on the quality of the mesh, and you have to know how the mesh should look like. Okay, so the mesh can be different, yeah. The most important is you have a mesh on the model, yeah. The mesh is composed from elements 1, 2, 3, 4, 5, 6, and so on. It means these are elements, and here are nodes. The nodes are not visible now. All of us have the mesh. Any mesh, not exactly
Yes.
the same, just
Yes, yes.
mesh, yeah?
Yes, I have the mesh.
Okay, so here on the right side here of the graphic window, I can switch the nodes on. Yeah, now the nodes are visible. Yeah,
Where is this? Come again?
here on the right, I'm clicking here on this icon.
I can't see the mouse. Where did you put it?
Sorry. Can you see now the right part of the window? Yeah,
Yes.
this one. Toggle node display.
Hover and the name will come out. Just hover on top of it. You see the name.
The white box with the red top red. White box, red top red.
Here. So if you generate the mesh, you have the nodes and the elements. Yeah, these points are the nodes, and these are the elements. Yeah, and it's necessary to understand that in the finite element method in elasticity, if you are solving the problem, the main result of the finite element method is displacement of the nodes. That means if we have the mesh, the result is displacement of each of these points. Yeah, because we will work in 2 dimensions, each point has 2 components, x and y component of its displacement. That means if we have, for example, 1,000 nodes, I don't know how many now we have, yeah, but 1,000, the result is 2,000 numbers, the x and y displacement of the first node, x and y displacement of the second node, and so on, and so on, and so on. Yeah, that means from this is, I think, a little bit clear what does it mean, a good mesh. A good mesh means there are enough nodes in the regions which are interesting for me. Yeah, if the mesh, if you have only few nodes in a region which is interesting for you, then you have only few results in the region. Yeah, that means more nodes mean a more precise result. But more nodes means also more unknown values. That means a huger system of equations, huge matrices, and a longer solution. For such simple model, the solution such simple model will be solved in 2 seconds, yeah. But a complex model can be solved 2 weeks, and then it's quite important. Imagine where it's important to have many nodes, a coarser mesh, and where it's not so important, because if you have too many nodes, the model is too big and you can wait for the result very, very long. Yeah. So these are, I will switch the nodes off again. So we have now this model with these elements. Here on the right side, we have this icon C and this icon T. For us, it's important to see its so-called node element class. The class of our element is quad4. It means each element is a quad with 4 nodes.
Is it with symbol C or T?
C.
Yeah.
Class. C is a class, yeah?
Yes.
Again, from the geometry, it's known that this is so-called a linear element because it has 4 nodes, 1, 2, 3, 4. Yeah? Each element has 4 nodes. For the quality of results, it's much more better use quadratic elements. So now it's quite useful on our mesh, which is composed of this type of elements, of the linear elements, change to quadratic elements. So now here on the operations on the top, we have change class.
That means the nodes are quadratic, right?
No, the elements are linear. Nodes are just points, yeah? Nodes are points.
Okay.
This is a node, this is
Because
square.
in mine it's represented like a quadratic. Nodes.
The elements, each element is described by his node. That means this element is described by these 4 nodes, for example. Yeah, and if the element is linear or quadratic, means the interpolation of the displacement inside the element between these 4 points is linear.
Okay, yes. Because it's
so
very small. And when
this
it's
point
small,
has displacement 5, this point has displacement 7. That means that the interpolation between these 2, 5 and 7 is a linear function, just, yeah? Because we know the result only in this point, and between the nodes, we have to interpolate, yeah? And the linear interpolation, or the linear element, means the interpolation is linear. But it's much more better is to use quadratic interpolation. That means we can switch to quadratic elements, yeah, and we can make it using this change class. So we can click on the change class. I can close this mesh, it's not important. Again, yeah, change class, and we have this window now.
Yes.
And we can switch to quadratic elements here on the top.
Okay.
And now we are asking the element list, and we can change all elements. That means we can click all existing here. and we can read number of unchanged elements 0, and changed elements 5, 3, 8. In your case, the number can be different, of course.
Yeah, mine is 1,470.
So you can see that the number of nodes is greater now. Yeah, because these nodes. Yeah, because now it's because for quadratic interpolation we need 3 nodes, of course, in each line. Yeah, so now we change the model to quadratic, and the class now is quad 8. Here you can see here is the 8. Yeah, that means it's a different class of elements now. Yeah? So now we have the model with a mesh and with quadratic elements. I will switch the nodes off better now. So we have this one. So now we have the mesh. In general, in finite element method, we are working in 3D, but in this special simple case, we are working in 2D. So here on the top, here we can see analysis, 3D.
Yes.
And we will change it to the planar analysis.
Okay.
Yeah. So now we are just working into XY, just in this plane. Yeah, not inside. So this one, and this is in fact a part made from steel and so on, and of course it should have his own thickness. This, yeah, it's 1 millimeter or so on, yeah, anything like that. So now we have to continue, and we have continue with the next card, not tables, but geometric properties. So I switched to this card, geometric properties. Yeah, this is a planar problem. Yeah, but if you want to solve a stress, you have the third dimension. Yeah, the thickness. Yeah, so I will put here new plane stress. That means it's a planar problem with planar stress. Of course, we can solve a planar problem with plane strain, but if you watch to the Hooke's law, the plane strain and plane stress are different. So I will choose plane stress. So once more, geometric properties, new plane stress, click, and we have new window again. And now we have to add the geometric property, and we can see the thickness. Yeah. For example, 1 millimeter. Okay. Maybe.
Yes.
Okay. And we can change the name of the geometric property for us. Sometimes it's much more better to give a name. So I can write, for example, T thickness. Yeah. Up to you. Now, in this moment, we just defined the geometric property called T with value 1, but now we have to assign this to our model. So now we have to add elements with this property. Okay? So add.
Yes.
And now which elements? All existing.
Okay.
So in this moment, all elements has 1 millimeter of thickness defined. Okay. Yeah, and we can see geometric properties here in the model, in the tree of the model. Structural stress, structural plane stress, called T. Yeah. And if I closed it, and now using double click, I can open it again and edit and so on. Yeah.
Mm. Yes.
Yeah, so I can change it if I want and so later.
Yes.
So now I have the geometry, the mesh, and the thickness. And the next step is, I think, boundary condition. I have fixed, we will start with this one. Sorry. So we have the body. We will fix the left end. Yeah, so this end will be fixed now. Yeah. So
Okay.
now we have to apply a boundary
Only one side.
on the left side. On the left side. Yeah.
Okay.
On the left side.
Yes.
So now we will continue with boundary condition. This is discard boundary conditions, and we will work with the left end. So I will zoom left hand. So, and now boundary condition, new, fixed displacement.
Boundary condition, then new general, new state variable.
Fixed displacement, yeah.
Yes. One window appear.
Yeah. Again, I can change the name. So for example, fix, yeah, enter. And I want fixed displacement in the X and Y direction.
Okay.
Yeah. So X is 0,
Yes.
Y
20.
is 0. Okay. Rotation is not important now because the elements cannot rotate.
2D.
The nodes cannot rotate. The nodes are just points. Yeah. So we are applying just nodes. Yeah. Okay. And now I want to apply this boundary condition on the nodes on this line. Yeah.
Yeah.
They are not visible, so I can switch them off, switch them on. Yeah. And nodes, add, and enter apply node list. So I can click each of these nodes, or I can, using the left mouse button, make anything like this. Yeah, and you can see the list is here. And using the right mouse button, I will confirm it. Okay.
I don't have it.
I will undo. So 0, 0 here, displacement.
Yes. Yes.
Nodes, add.
Yes.
And now I have selected nodes with this boundary condition. I can use the mouse. The hand should be switched off, this one.
Yes.
Not
It's
so.
selected.
Not so.
Yeah, because I was putting the left hand on.
Yes,
That's why it doesn't work.
Yeah, and now you can draw such rectangle.
Yes.
Okay,
I did it.
Selected now. You
Yeah,
can see
then it become like
right
that.
mouse button, confirm.
Yes. Now it's true.
You can see here this arrowheads, yeah. And
Yes.
here is the number of nodes to which the fix is applied. Yeah, in my
Yes.
case it's 11, in your case a different number. Yeah.
Yes.
So now we fixed the left end of the model. Okay.
Okay.
If you can see here in the model 3, we have a new boundary condition, fixed displacement called fix. Yeah.
Yes.
A new set here, a new set of nodes, and the set is called fix nodes, and this is the set of nodes to which the fix is applied. Yeah, it made the software automatically. Yeah, that means these are these nodes. So now
Yes.
we just made a boundary condition on the left end of the body. And now I will switch to the right end of the body. So I use the hand now, and now we'll switch the hand off again, so that the selection will work. And now on the on the right end of the body, I will describe displacement in the x direction.
Only in x direction.
And the x direction, yeah, that means the body will be longer, yeah. So
Okay.
boundary condition again,
Yes.
mu, fixed displacement again,
Yes.
what do I, for example, displacement. And now we have to add a value of the displacement, yeah. How long they will be displaced, yeah, on the x direction.
Yes.
So displacement x, for example, 10, okay, 10 millimeters, okay.
Okay. Okay.
You apply to
Did you use
know
the value 10?
value x displacement here, yeah,
Yeah, 10, okay.
10, yeah. Just why not, yeah, 10, okay. And we will apply to nodes. That means nodes, add, and again we have to choose the nodes. And right mouse button. Okay. So we have the displacement 10 in the x direction applied to these nodes on the right end of the body.
Okay.
Okay. And we have two displacements, fix and disper. I wrote dips. Oh, never mind.
But the displacement is written. It's drawn here inside the beam.
Never mind. Never mind. Because it's applied to this node in this direction. It's okay.
Ah, it's okay. Okay.
So I have just watched in this table. Yeah, it's plus. It means it's in the positive direction.
Okay. Okay. Yes. 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 Yes.
Okay. Yeah. So we have now these two boundary conditions, and now we can see it's fixed. Yeah, where the left end is fixed, the right end is moved to the right by 10. So this is defined. Yeah, and now the next step is we have to define the material. Yeah, because this is also not given.
Okay.
So we skipped the material, and now we have to go here in the material properties in this card here in the middle.
Yes.
And again start with new.
New.
And fine and stiffness standard. Yeah, there are many options, but for us it's the first one,
Standard.
the best now. New fine and stiffness region standard. And we have a new window, a great window now.
Yes.
And I will make, for example, steel, mass density here. Because we don't work with gravity in this example, it can be 0. Yeah, it's not important. Without gravity, okay. Young modulus 2.1 E5 megapascals. Poisson's ratio 0.3. Okay, and we can. Sorry.
How much Poisson ratio?
0.3.
1.3.
Yeah.
Okay.
And we can choose on plasticity.
Plasticity, yes.
Plasticity. A new window again.
Yes.
Switch on.
Plasticity, yes.
And now many options, and yield stress is for us the most important. So for example, 250, yeah.
How much?
250.
Okay.
Okay. So now we have a material called steel with Young modulus and Poisson's ratio and with yield stress.
Yes.
And now we have add this material to our model.
Okay.
Add to all elements. That means elements add all existing.
Yes.
Okay. We can close it. So in this moment, I think it's everything okay. And
Yes.
we can continue with to the solving. Yeah. So the next step we need to make is a load case. Here on the right, load case here, new load case,
What?
static load case,
Load case, new. Static.
static.
Yes.
And now this is the name of load case, okay. And loads which are applied in the load case.
Yes.
It's fixed and displacement. We can choose different, maybe we can have a huge set of different boundary conditions, loads and so on, and we can switch in the load case different on, off as we need. Yeah. In this case, we have only fixed and displacement, so all of them are here present. Okay. Okay. Yeah.
Yes.
Fine. And the rest of the load case here, this this one, it's not important. No, it's important, but not now. Yeah, because there are many possibilities how to make it wrong. Yeah, so leave it in the default values.
And
So,
in this window, you only check the fixed and displacement. That's all.
yes, I only check that this is switched on.
Okay. Yes. Yes.
By default, it is. Yeah.
Yes. Yes.
I
Yes.
can change it if I want. I just create it. Yeah. If I.
Okay. Yes.
Yeah. So we have the load case now here, and the last step is job.
Jobs.
New structural job.
Yes.
And we have a new window again. Job 1, for example. And here in this part of the window are load cases which are valid for our job. Here is nothing. So we have to choose this load case and we will move it from bottom to top. That means this job will be solved with this load case. Yeah, we can, in general, we can have, we can prepare many load cases and we can choose the load cases. Yeah, here can be a list of load cases and we can put it as selected load cases. Yeah. So now
I can't see that window.
Yeah, but sorry, but the Windows is too.
No. I mean that one. It's something was written there.
Yeah, job, load,
Yes.
Job, new, structural,
Yes.
and you will get a new job.
It's empty, right?
You click on load case.
Yes.
There is in the model is nothing. Yeah, now in my model, and if I create job new structural,
okay,
I will get this window.
Yes.
And now I will choose the load case for job. The only.
Okay. Yes. Now it's appear here.
Okay.
Yes.
Perfect.
Okay.
And now it seems it is okay, so I can click on check here.
Okay.
And if it is everything correct, no errors, no warnings here.
Yeah, it's written 0 warning.
Perfect. Yeah. So we can click on run.
Okay.
Another window. The job I can close now. It's not important. So now we have the run menu.
Yes.
And there are many possibilities again. But the only thing on this, we will click on submit. That means after clicking this one, the MARC, the solver, will start on the background and will solve the model we prepared using Mentat. Yeah. So
Yes.
Mentat is this our window. We prepared the model using Mentat, And so using submit, we will send the problem to MARC, to the server, and this will solve. So submit,
Yes.
and we have to wait for a minute. And here is an exit message, 2004. And this is wrong. Because the exit message, the correct exit message is 3004. Yeah.
Yeah,
Click.
it shows his exit number is 3004.
You have 3004?
Yes.
Okay, so good. I think you you have anything different in the model. Maybe it's given by the mesh, or it's given you have the yield stress in the material and so on. Yeah, never mind. Okay. Yeah, because I think the mesh is different. Yeah, so exit message. You can click on this one, and you will get explanation. What does it mean? Okay, if you have 3004, it's okay. You have it's okay. I have not the cost because I prepared this example to show you potential problems. Yeah, so I prepared it that my results are wrong at the start. Yeah, and now I have to go back and repair what I made wrong. Yeah, if your result is okay, so it's okay. Yeah.
Yeah.
But now we have 2 o'clock, and I have another lesson in 10 minutes, so I have to finish for today.
Okay. Yes.
I hoped we will be a little faster, but never mind. So we will continue next week from this point. Yeah.
How can I get the result now?
Okay. Yeah. If you want to see the result.
Yes. Yes.
I cannot do it because I have not the result. Yeah. But you can open post file.
Yes.
And then the method will open the file with the results, and here in the results you can open this this model plot. This model plot. Yeah, I cannot do it because I'm not the results.
Yes. Okay.
And then you can try what you can see in your results. Yeah.
Okay. Yes.
I got 2004 just like you, but still I had my bar default.
There is a problem, but I have not more time to explain why the problem is and how to repair it. So we can continue. Sorry, we have to continue next week. Yeah. So so that's all for me for today, and see you next week again. I will send you the classroom again by email, and we will continue.
Okay.
Okay.
Thank you.
So
Thank you.
that's all for today, and bye.
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 Thank you.
Bye.